over here, I've written part of the function f of x equals the square root of x plus 1. And today, we're going to be using definite integrals to find the volume of this function if it was rotated about the x-axis from the points 1 to 4. So when I say rotated about the x-axis, I mean it's going to be making a sort of 3D shape when we do it. So let me see if I can draw it. I'm sure my drawing is going to be quite terrible because my hand's a little shaky. But basically, we're going to be filling in all of that area there. But it's not just 2D area, right? It's making an actual figure. And the figure it's going to make, let me pull out my highlighter here. The figure it's going to make kind of cylindrical in shape. And we're going to try and find the area of this solid that we have just made. And we're going to be using an integral to do that. So first, let's remember what an integral actually means. An integral will find the area under the curve, right? So it'll find this area right here, from the curve to the x-axis. So now let's see if we can use this to find the area of the solid. And so let me write out the formula and then explain what the formula is doing. So pi times the integral of a to b f of x squared dx. Now, what's important to remember for this formula, or to figure out why it works, is that the area of a circle is a equals pi r squared, right? So what you're doing here is this cylindrical shape, right? It can be broken up into little tiny circles, right? Little tiny cylinders. And these ones, you find the area of each one and you add it all together. And infinitesimally small, right? And that's what this integral sign means. It means add up all these little tiny areas. And that'll give you what the area of the whole function is, right? Because all of these together, all of these right here. So that's basically what the formula is doing, and we're just, find all of the areas of these circles from the points that you decide, from A to B. So now let's find the area of this specific function, right? We want to find this area from 1 to 4 of the square root of x plus 1 squared dx. And we can pull the pi to the outside just because it's a constant. It's just a number. And so now this should give us our area of this solid that we just created using the disk method. Let me write that up here so you know this is the disk method formula. All right. So let's integrate this. So you could use a calculator and use Math 9. I'm going to go ahead and integrate it by hand just because this is really, really simple. And I guess it'll be a little refresher on integration. So these right here, these cancel out. So what you're really left with is pi times the integral of 1 to 4 x plus 1 dx. Now the antiderivative of x is 1/2 x squared plus the antiderivative of 1, which is x. And you're finding this from 4 to 1. And now we know that we need to find the antiderivative of f minus the antiderivative of 1. That's the fundamental theorem of calculus. So let's find this 1/2 of 4 squared plus 4 minus 1/2 of 1 squared plus 1. And this, hold on just one second, let me give us a little bit more room here. So 4 squared is 16, half is 8, plus 4 is 12. Hold on a second, 12. minus 1 squared times 1/2 is just 1/2 plus 1, and multiply all this by pi, right? And so 1/2 plus 1 is 3/2. 12 times 2 is 24 over 2 minus 3 over 2. And this will give you 21 over 2 pi. And this right here is the area of this solid up here that we made, right up here. Yes. So that's how you find the area of a function using the disk method, right? That's how you find the area of a function if there's just one function and it's being just revolved around the x-axis. But next we're going to look at the washer method, right? We're going to see, hey, what if there is more than just that one function? What if the function, whenever it's revolved around the x-axis, gives you a solid with the hole in the middle, right? That's when we're going to have to use the washer method. And we call it the washer method because it kind of looks like a washer, you know, in that it has a circle in the middle and then it has a solid surrounding it. So let me draw out a function for you, an example function here. So generally you're going to have two functions here that are working, right, to make it a washer method. This right here is going to be f of x equals x squared. And then we're also going to have g of x equals x. And do you see, hold on one second, do you see that little area that is enclosed right there? Right here. See, it's too small even for my highlighter. Well, we're going to see that revolved around the x-axis. And so the washer method, the formula for that would be kind of similar. What the heck? That's not the right color. It's going to be kind of similar to the disk method, except now it has 2 in it. So the integral from a to b of f of x squared minus g of x squared, right? And what this is, f of x and g of x, it's not necessarily these right here, right? You determine which one's f of x and you determine which one is g of x by finding the outside minus the inside, right? Because that's how you find the area under the curve. And so it's just like finding the area under the curve, except now you're finding the area of the solid instead. You know, that's why you have pi, and that's why you square the functions. And so for this particular one over here, I'm going to go ahead and put the limits of 0 and 1 on it, so we don't have to find that. And so I'm going to go ahead and find what the solid of this revolution would be, right? And let me go ahead and map it out for you. I guess I did that last time. That's where you get this thing, you know, kind of like this, except it's only going to be the area of this right here and this up here, except that's going to be like the solid form of that. So it's going to be basically the outside here, but the inside here is going to be empty. Like I was saying, it's like the washer method. It looks like a washer. I don't know, that probably just confused you more, but that's what it is. And so let's fill this out. So if we're going from 0 to 1, then f of x is going to be the outside function, which here is x, because you can see how x is on the top and x squared is on the bottom. So x squared minus g of x, which is the inside function, which is x squared dx. I guess I should have thrown dx up here too to make it, you know, how it should be, like official. And so now let's go ahead and find what this actually is. So you could just throw it in a calculator. I'm probably going to do that eventually, but let me just solve this one out by hand. 2 pi times the antiderivative of x squared, which is 1/3, x cubed, minus the antiderivative of x squared, which we know because of exponent rules that x squared is x to the 4th. So the antiderivative of x to the 4th is 1/5, x to the 5th, right? I'm going to find that from 1 to 0, so pi times 1/3 of 1 cubed minus 1/5 of 1 to the 5th, right? And then we're going to do minus 1/3 of 0 cubed minus 1/5 of 0 to the 5th, right? And this right here, we know 0 cubed is 0, minus 0. This is all going to go to 0 right here. So we're just left with pi times 1 cubed is 1, 1 to the 5th is 1. So 1/3 minus 1 to the 5th. And that can also be written as 5/15 minus 3/15. And this, times pi, of course. I'm going to throw that back here just because I forgot. And then this is going to give you 2/15 pi. So this right here, once again, this is the area of this solid of revolution right up here. Sorry, that really was a bad job drawing, but if you can visualize it, it really helps. It really helps you get it. So I would encourage you to look up a video of somebody else like visualizing it, or somebody else drawing it out so that you can see. And so I'm going to do an example from a released AP Calculus BC exam. So that you can see something that would be that was actually officially done by people when they were testing their calculus skills. There are none that I have found anyway that test over just the disk method or just the washer method, right? They're always about a line in all of the released free response questions. So I'm going to do an example of revolving a solid about a line, about the x-axis line, because it's pretty similar. It's pretty similar in what you do and why the formulas work the way they do. So yes, let me draw that out for you really quickly, and then I'll explain how basically you're going to use the washer method, just modify it just a little bit. So this one is from the 2004 AP Calculus BC exam. 2004. And this is question number 2. If you want to go look it up, you can. So what this question is asking you is to find the solid of revolution of this graph about y equals 2. So let me draw out the graph for you here. That's 1. And there. This top one is y equals f of x. And this one is y equals g of x. Let me clean up that y just a little bit, sorry. Alright, now, f of x and g of x, let me go ahead and define that, so that it actually means something. F of x, I'm going to do this in a different color too. I know black is getting a little overused here. F of x equals 2x times 1 minus x. And g of x equals 3 times x minus 1 times the square root of x. Alright, So these formulas are a little more complicated than the one I showed you before, but you know, what you do with them would be essentially the same. And so when they ask you to revolve it about y equals 2, they're asking you to revolve it about up here, right? And so you revolve this area right here about up here, and it's going to give you the same thing. It's going to give you a solid with a hole in the middle, right? It would be up here-ish, and then you would do, you know, that right there, leave that spot in the middle blank. So you do basically the same thing, except now we call it r's, right? Sorry, let me change the color here. Back to good old black. Pi times the integral of a to b, big R squared minus little r squared. So to find big R and little r, we're going to need to find what the area, or sorry, what the length is from the line that they gave us, which is 2. And so let's just think here. We need to get this middle section revolved about. And so what you're going to need to do is put up something a little bit like this. Oh, also, sorry, one last thing. They actually bounded it from 0 to 1. That's why, I stopped it right there. That makes it, easier. If they didn't do that, you would have to find where the points intersect and all that. But in the equation, in the question, they bind it. So we're going to go ahead and do that as well. And so let's do pi times 0 to 1, right? And now big R and little r, let's find this. I'm going to write it out first, and then I'm going to explain it. So big R is just 2 minus 3 times x minus 1 root x squared. All right, minus 2 minus 2x 1 minus x squared. Right, let's go ahead and throw a dx on there. All right, now this will give us the area of this solid of revolution. Now, how did we know that it was 2 minus 3x minus 1 root x, right? How did we know to use g of x as the big X and this, as the big R and this in the small r? Well, what the big R and the small r is it's big radius minus little radius, right? The big radius, let me pull out a different color. The big radius would be the 2 to the bottom of the function, and then the small radius would just be this right here, right? And so to find the small radius, we know that 2 would just be the area from 2 to the x-axis. But we need to take away from that f of x, right? Because that's what's stopping it from getting there. So 2 minus f of x would give you the small radius, which is what we have over here. 2 minus 2x, 1 minus x, which is f of x, right? And then to find the big radius, we would find. And so if this was a solid function, right? If it was just g of x and it was revolved about this line, it would be a full figure, right? But we know that it can't be that, right? Actually, to find out what this is going to be, it's going to be 4 minus, it's going to be 2 minus g of x. And so that's what we have over here, 2 minus g of x. Sorry, I kind of explained that backwards, but that's what it is. And so this right here, all of this over here is how you would find the area of this solid of revolution about 2. And so, let me go ahead. You could solve this out by hand, but I'm a little bit lazy. So, I'm just going to throw that into the calculator, and then we're going to see what that is. So, hold on just 1 second. And if you have a calculator, this is just going to be math 9. But if you plug that in, you're going to get 5.15 pi. And so this is, you could either write that as 5.15 pi, or you could just write it and simplify it to being 16.179. Either one of these, these say pretty much the same thing, except this one is less accurate, but it is in decimal form. So if you want that, there it is. That is how you would solve this problem. It's a washer method problem, but it's about a line, right? It's not just about the x-axis like this one was, or like this one was with the disk method. And so that was the disk method and washer method, and the washer method about the x-axis.